Thank you, Rachel. So, yes, I'm Sonya Fiddes. I work for the Australian Antarctic Program Partnership, and this talk I'll be looking at aerosols in the ACCESS-AM2 model. And I've got a big list of collaborators there who I'd like to acknowledge. So, I know a lot of people in this room probably have never thought about an aerosol in their life, so I'm just going to start from the start. Aerosol are tiny particles, liquid or solid, suspended in the atmosphere, and when they're big enough, they provide a surface for water to condense onto, and this is what forms a cloud. Okay? This is a video that my colleague Mark took recently on the RV Investigator right at the Antarctic coast. It's a very dry and clean place, so he's got a cup of tea which provides moisture, and a lighter which provides an aerosol, and you can see when the two meet, we get condensation and a cloud forms. So that's sort of the process. So aerosol interact with sunlight directly or indirectly by changing the properties of clouds. They can make them brighter, higher, longer life, change precipitation rates, things like that. So that's why we think they're important. They come from a range of sources, different sizes, and undergo a range of processes. So for the Southern Ocean, where I'm focusing this talk, most of the aerosol are from natural sources, which includes from phytoplankton through processing, producing dimethyl sulfide, and sea spray, which produces sea salt and primary marine organics. So why do we actually care? Climate models, which includes ACCESS, the CMIP models, ERA5, actually included in our satellite retrievals of radiation, they all have this large radiative bias over the Southern Ocean. You can see it's the worst in our summer. This big bias here, the red, basically means that too much sunlight is reaching the surface of the ocean, which can cause warm biases. It can affect other parts of the physical system. So we're trying to improve or reduce this bias by looking at the cloud aerosol interaction. And we know that this is an important part of this story from our IPCC reports and other studies. We can see that aerosol-cloud interaction actually has one of the largest uncertainties for our global radiative balance. So you can see, if you just look at the error bars in both of these plots, the aerosol part makes up one of the biggest uncertainties. So a lot of this is because we don't actually know enough about natural aerosol, and the Southern Ocean, being one of the cleanest places on Earth, away from anthropogenic sources of pollution, is the best place to try and study this. So, we're evaluating ACCESS, and I've run a range of experiments as well to try and improve the aerosol representation. I'm looking at two different types of aerosol sizes, so one that includes aerosol from very small to very big, and one just looks at the very big, so we've got N10 and CCN, that's cloud condensation nuclei. We've got observations from a whole lot of field campaigns. So we've got 3 long-term stations, Kennett, Cape Grim, at the northwest tip of Tasmania here. We've got Macquarie Island and Shoa, which is the Korean Antarctic base. And then we've got a range of ship campaigns on both the Aurora Australis and the RV Investigator, transecting the Southern Ocean. The model that I'm using is ACCESS-AM2, so it's the CM2 model without an ocean. In the place of an ocean, we have prescribed sea surface temperatures and sea ice concentrations. It follows the AMIP protocol using the HAD-ISST data sets. We're running from 2015 to 2019 to coincide with these field campaigns, and we nudged to ERA5 so that we can compare day for day. Our meteorology is as close to reality as what we can get. And of course, we're using the GlowMap aerosol scheme, which is turned on by default in CM2, but not in ESM, so if you were interested. I've run 8 simulations. I'm not going to go through all these because I'm a bit short on time in this talk, but basically we have a control run, which uses a GA7 configuration of the model. We have another control run which uses the ACCESS configuration, and the only difference is the dimethyl sulfide climatology. Runs that will stand out is the boundary layer new particle formation, which is basically when a gas Instead of condensing onto an existing particle, it condenses to form a new particle in the boundary layer. We turn on marine organics. We test new DMS climatologies. We've tested a climatology with OM2, but I'm not going to go into that. And we've done a combination of the primary marine organics and DMS. And we've also done one where it's a bit of more of a test rather than something that's actually physical, where we change the sea spray flux parameterization to use the wind gust rather than the mean wind speed, just so that we could really boost the aerosol numbers. So there's a lot on this slide, I apologise, but basically all I want you to take away is that the black line are our observations and the coloured lines are our model runs, and we can see this is for the N10, which are aerosol that are from small sizes all the way to large. Our model does quite badly. We really underpredict these aerosol numbers, and this is true for all three stations, which are on the left, and the voyages, which are split up by season and latitude. So we can see it's a fairly consistent story across the board. For our experiments, if we turn on the boundary layer new particle formation, we get a lot of new small particles, but really only areas that are closer to land, to Australia, so these northern regions. And we think that's because of the way the nucleation particle scheme works. I won't go into that. The only other one sort of any interest or any major change is the sea spray flux, which is here. For more marine-based regions like Macquarie Island, it has a small impact on the N10. If we look at the larger aerosol, it's a pretty similar story. We actually overestimate CCN at Kennedy Cape Grim here. But for the more Southern Ocean and Antarctic regions, it's a similar story of heavy underestimation. Oops, my mouse is now upside down. Okay. And again, our boundary layer, new particle formation change, and our sea spray flux change have the largest impacts. Turning on our primary marine organics and changing to a new DMS climatology also does improve CCN. I'm sorry, you can't really tell from these plots because there are a lot of lines, but you will have to trust me on that. And combining both of these two simulations here results in a still improved CCN, but slightly lower than the two individual runs. They kind of cancel each other out in a way. So, if we were only interested in CCN, which is aerosol that are climatically relevant size, we might say, okay, adopt the change to the sea spray flux. But we know this parameterization isn't really that physical, so it might not be that good an idea. Turning on the primary marine organics and updating to the most recent DMS made differences in CCN, but we think this is for the right reason. Thank you, Rachel. And we want to explore this a little bit further. So we're looking at the radiative impacts that these changes in aerosol make to our model. So this is the annual mean, in this plot here, this is the annual mean radiative bias. You can see our Southern Ocean bias here in blue is standing out a bit less when you look at the annual mean. If we look at our sea spray flux change, we actually make most of the world a lot worse in terms of its radiative balance. So this is not going to be a good thing to recommend in a model. Even though we improve our cloud condensation nuclei, we're making the energy balance much worse, which is, I think, in my mind, a real problem for us. If we update the new DMS climatology, we're seeing some improvement in the place that we want, but it's extending a bit too far north. And if we update to the primary marine organics, we again see some improvement where we want, and it's more constrained to the area that we want it. So this is a potential possibility of actual improvement. And if we break this down into seasons, if we just especially look at our summer, this is the actual bias, and this is the change between the control and that simulation. We can see most of the change is concentrated in this region where it's the bluest of the blue. So we're quite happy with that, and we've only got sort of compensating errors happening in the springtime. So to conclude, we're quite happy with the changes in primary marine organics with the new DMS climatology. It has improvements for the Southern Ocean with only minor impacts elsewhere. So we'd recommend to test this for AM3, and the other reason is that it brings it more in line with newer configurations of the turning on the primary marine organics, so it's nothing crazy. And the other thing to point out is when we actually do have more realistic CCN values, like in the sea spray flux parameterization, we ruin the other parts of the system so much. So this points to either really significant issues with tuning or really significant microphysical problems, and it's probably both. Thank you.
Any questions? Martin?
Sorry.
I would have expected with more sea salt CCN you would have had brighter clouds and got the opposite effect. So do you know what's happening to the cloud?
Yeah, we see more liquid water path and we see a greater cloud fraction. So I think I haven't dug into it really deeply, but I think
again, you'd think there'd be more reflection rather than less, but with that.
Now I have to think about all my biases. It is reflecting more because we're increasing the amount of shortwave radiation being reflected out to space in that run. So it's doing the right thing that we want it to do in the Southern Ocean, but it's not doing it in the places that we want it to, basically. Yeah.
Thanks, Sonia. I might have missed it. So you were nudging to the meteorology in all your runs? So have you...
We expect the meteorology to be the same across the same.
So I'm wondering if you now just did a free running experiment, like if there's any feedbacks between the meteorology and your changes?
There certainly could be. That makes it extremely difficult. I think I spent a whole year of my PhD fighting with that exact problem. Yes, so when you run with free running, you're allowing a lot more other things to happen, and it makes it really difficult to actually pin down the changes to what you've done in a way. So you need to start then thinking of ensembles, and then you start, making your workload a lot larger. Yep.